я за это сяду, но мне хочется в какой-то момент сесть и отскринить. Много деталей, они забываются.
Надо начать. На всех случаях проверим, хотя там с этой трансляцией последнее время что-то непонятное происходит.
Я так понял, что в последнее время не было той лекции, которая перед нами, а сейчас она была. По крайней мере, я точно видел ее на трансляции.
К3 есть, да.
Видимо, он как-то так запрограммирован, что после К3 запускается Topological
Вот,
Spaces.
сегодня вроде бы оно уже пошло. Ну хорошо. Значит, можно начинать, наверное.
Ну да, по времени-то уже 5 минут как надо начинать.
Ну отлично. Okay, so in the previous lecture we discussed complete local economic spaces. And at the very end of the lecture we introduced the notion of completion. So let's recall what it is. If X is a local economic space, then the completion of X is a pair consisting of a complete local economic space X tilde and a continuous linear map J from X to X tilde, which has the following universal property. So for every complete local economic space Y, and for every continuous linear map from X to Y, there exists a unique continuous linear map from X tilde to Y, such that the diagonal commutes. So X tilde is also complete. Okay, so this is our definition. The definition here already implies the uniqueness. That is, you have two completions, say X tilde and X hat, with respective maps, so J and J prime. Then there is a unique topological isomorphism between X tilde and X hat, such that the diagonal commutes. So if the completion exists, then it is unique in this sense. I'd like to stress that a priori we don't assume that J is injective, and we don't assume that its range is dense, and we don't assume that it is a topological isomorphism onto its range. However, many of these statements will follow automatically. Actually, we will see shortly that if X is Hausdorff, then the completion exists, and J is a topological isomorphism onto a dense subspace of X tilde. Well, at the end of the previous lecture, we reduced the problem of constructing the completion to the case of Hausdorff spaces. So if X, so let's recall that if X is not Hausdorff, then we can form the so-called associated Hausdorff space XH, which is just the quotient of X modulo the closure of zero. This space is Hausdorff, and roughly has the same completion as X. More exactly, if we have a complete locally convex space X tilde and a continuous linear map J from XH to X tilde, then we observe that X tilde together with J is a completion of XH. So this happens if and only if the same space X tilde together with the composite map of these two arrows. So here QH is just the quotient map. So this is a completion of XH if and only if X tilde together with J composed with QH is a completion of X. Now this is more or less immediate from the definitions, because once we have a continuous linear map from X to Y, where Y is complete, first we can quotient it out, we can factorize it through XH by using the fact that XH is Hausdorff. So the closure and y is Hausdorff, so the closure of 0 goes to 0. And then if x tilde is a completion of xh, we can further factorize this map through x tilde. And this implies that x tilde will be also a completion of x. Okay, so now we see that everything is reduced to the case if we want to prove the existence of a completion. We see that it's enough to construct this for Hausdorff spaces. And we have the following simple proposition. If x is a Hausdorff locally convex space, x tilde is a complete locally convex space, and J is a topologically injective linear map. A topologically injective linear map with dense range, such that the closure of J of x is x tilde. Then x tilde together with J is completion of x. Now this is immediate from the extension by continuity theorem, which was discussed in the previous lecture. Extension by continuity. Theorem. So since J is topologically injective, we may think of X as a dense vector subspace of X tilde. And we know that every continuous linear map defined on a dense subspace of a locally convex space and with values in a complete locally convex space can be uniquely extended to the bigger space. Okay, as a corollary of this result, we see that if X is a norm space, and if we have a completion of X as a norm space, then the same space X tilde together with the same map J will be a completion of X in the class of all locally convex spaces. As a locally convex space. Well, indeed, I'm assuming you know what a completion of a norm space is, and in particular, it is a Banach space X tilde together with an isometry J onto a dense subspace of X tilde. So the conditions of this proposition are satisfied, and we conclude that X tilde is a completion of X as a locally convex space. Okay, let's now try to construct completion. So we start with Hausdorff locally convex space X, and we choose a directed defined family of seminars. So now for every seminar P from our family, we do the following. We denote by XP the quotient of X modulo the subspace where P vanishes. It's clear that from the triangle inequality that this is indeed a vector subspace. So we may form the quotient, and we consider this quotient as a norm space with respect to the quotient norm of K. It's easy to see that the quotient semi-norm of P will be norm of the quotient. So this will be a norm space. This is a norm space. And let xp tilde denote the completion of this norm space. Okay, now we have the following picture. This is x. Here we have a quotient map from x to xp. That's denoted by pi p. I'd like to stress that this is not a quotient map in the topological sense, because xp, the topology on xp is not the quotient topology. The topology on xp is denoted by the only norm p hat. So pi p is, of course, pi p is continuous, but in general it's not a quotient map in the topological sense. And xp is embedded into xp tilde. So the composite map will be denoted by phi p. Let's now observe that the spaces xp and also the spaces xp tilde form inverse or projective systems of locally convex spaces. Well, indeed, if we have two seminorms, p and q, in our family, such that p is dominated by q, then it follows that we have the following inclusion. This is immediate from this assumption. So we have a map. There is a linear map pi pq, which acts from xq to xp by the following simple formula. Simply because this subspace is contained in this one. So we can now look at the following picture. So this is x, this is xp, this is xq. Here we have the maps pi p and pi q. And here we have the map p pi q, pq, pi pq. Okay, and the diagram obviously commutes just by construction. Let's also observe that pi q is continuous. P pi q is, pi pq is continuous. Pi pq is continuous because it's bounded. So the quotient norm here is less than or equal to the quotient norm here. So it's continuous. Okay, now each of the spaces xp and xq are contained in their completions, xp tilde and xq tilde. And here we have the maps phi p and phi q. Now, since xp tilde and xq tilde are the completions, we can extend pi pq by continuity to xq tilde, and we get a unique continuous linear map phi pq such that the square commutes. Moreover, you have three seminorms, p, q, and r. P is dominated by q, and q is dominated by r. And then let's observe that we have the following equality: phi pq, phi qr equals phi pr. Well, indeed, this is true for pi pq and so on. So this is true on the uncompleted quotients just by construction. And by continuity, this respective equality extends to the completions. So we have this. And as a result, we see that the Banach spaces x tilde p, together with the maps phi pq, forms a projective system. projective system. Let's denote it by script x. And moreover, this picture shows that x, together with the maps phi p, is a cone over this system. Moreover, x, together with phi p, is a cone over script x. Okay, let's now form the projective limit. Let x tilde be the projective limit of this system. And let psi p denote the canonical maps from the projective limit onto the spaces xp. Well, now since x is a cone over this projective system, now by the very definition of the projective limit, we have a unique map from x to x tilde j. There is a unique continuous linear map j from x to x tilde, such that all the respective diagrams commute. This is phi p, this is psi p. So the diagrams commute for all p. Now I claim that what we've just constructed is exactly the completion of x. If x tilde and j is completion x. To prove that this is indeed a completion, we will show that the conditions of this proposition are satisfied. So we have to show that J is topologically injective and its range is dense in X tilde. To prove this result, we need the following simple lemma. Suppose that we have a projective system, say Zi, and tau and j, a projective system of locally convex spaces. Let Z denote the projective limit, and let tau I denote the canonical map from Z to Zi. Suppose we have vectors of space. Suppose Y is a vector subspace of Z. And suppose also that the image of Y under tau I is dense in Zi for every I. This implies that Y is dense in Z. The proof is an exercise for you. A hint is just recall how the standard base at 0 in the projective limit looks like. The standard base looks as follows. We take a base in every Zi and take the preimages under the respective maps. So the assumption that our index set is directed implies that the resulting family of neighborhoods of 0 in Z will be not just a subbase, but will actually be a base of neighborhoods of 0. And this easily implies the result. Oh, sorry, I said. Of course, it is always contained. Thank you. we assume that it is dense in Zi for every I, then I claim that Y itself is dense in Z. Okay, let's now prove our theorem. So first of all, it's clear that X tilde is complete, because we already know that the projective limit of complete spaces is complete, and by construction, X tilde is projective limit of bundle spaces. So it is complete. Next, if we now look at this picture, we see that our lemma applies, and it follows from the lemma that J of X is dense in X tilde. Well, indeed, if we look at J of X, we see that if we map it to XP and then take a closure, then this is the same as if we first take X to XP and then XP tilde. To XP tilde and then take the closure. But by assumption, just by construction, the image of X in XP tilde is dense by construction. So this implies that J of X, the image of J of X in XP tilde under psi P is also dense, and lemma implies that J of X is dense in X tilde. Now, let's now look at the kernel of J. Well, the kernel of J, by construction, is the intersection of the preimages of 0 under all semi-norms in our family. But this is 0 because X is Hausdorff. Since X is Hausdorff. So we see that J is ejective. Its kernel is trivial. And finally, let's observe that the topology on X, well, I have to switch to another blackboard. So the topology on X is nothing but the projective locally convex topology generated by the family phi P, simply because P is a defining family of semi-norms. On the other hand, the topology on J of X, is also the projective topology, projective locally convex topology, generated by the maps psi P, or more exactly by their restrictions to J of X. Well, indeed, J of X is a subspace of X tilde, and X tilde is the projective limit, so the topology on X tilde is by construction of the projective limit is the projective locally convex topology. And also, let me write once again the respective diagram. This is X, this is J of X, this is X P tilde, and the diagram commutes. So all these facts together, 1, 2, and 3, imply that J is a topological isomorphism of X onto J of X. Or in other words, J is topologically injective. Now this completes the proof. So we see that J is a topologically injective map onto a dense subspace of X tilde, and so our previous proposition implies that X tilde is indeed a completion of X. Okay, let's now look at some corollaries. Corollary 1, we see now that every locally convex space X has a completion. X tilde J. And moreover, the range of J is dense in X tilde, and the kernel of J is the closure of zero. In particular, this is trivial if X is Hausdorff. And finally, we claim that J is an open map onto its range. In particular, if X is Hausdorff, then J is topologically injective. Well, indeed, why is it so? Well, for Hausdorff spaces, we have already proved that J is topologically injective onto a dense subspace of X tilde. In the general case, we know that to get a completion, we have to, first of all, to replace X by the associated Hausdorff locally convex space, that is the quotient out to quotient out the closure of zero, and then to embed the Hausdorff space into its completion. So this readily implies that the kernel of J is the closure of zero in the general case. And moreover, this J, in the general case, this J is the composite map. First, we take the quotient map of X onto XH, onto the associated Hausdorff space. And then we embed XH into its completion. So the embedding of XH into its completion is an open map onto its range, and the composite of two open maps is an open map. So J is an open map onto its range. Okay, corollary 2, which is also useful. Suppose that X is already complete. Suppose X is a complete locally convex space. Then our theorem gives a very useful isomorphism between X and the projective limit of the associated Banach spaces X P tilde. A useful exercise is to describe this isomorphism explicitly for classical spaces. Exercise 1. Describe this isomorphism explicitly for the following spaces. First, for the space of all functions on an arbitrary set S. Second, for the space of continuous functions, C of X, where X is a locally, X is already in use. Okay, let's let it be, let's choose some another letter.
K.
T. No, K is something compact. And T is a locally compact Hausdorff topological space. The space of holomorphic functions on an open subset of Cn. For the space of smooth functions on an open subset of Rn. Five, the space little s of rapidly decreasing sequences, which is a discrete analog of the Schwarz space. So number 6 is the Schwarz space on Rn. Number 7 is a bit more difficult, but it's still solvable. So the space of compactly supported continuous functions on a second countable locally compact space. Number 8, the space of smooth compactly supported functions on an open subset of Rn. And number 9, the space of holomorphic germs at a point on the complex plane. The hint is that actually the respective projective systems were already explicitly written down at the previous lectures. So the exercise is to identify these concrete projective systems with systems of the form xp tilde, which appear in the proof of our theorem. Exercise 2 is about the functorial character of the completion. The assignment which takes every locally convex space to its completion is a functor from the category of locally convex spaces to the category of complete locally convex spaces. And this functor is left adjoint. Left adjoint to the inclusion functor of complete locally convex spaces. Complete locally convex spaces into the category of all locally convex spaces. Okay. Now we can prove a theorem which was stated without proof at the previous lecture, and which states that the strict inductive limit of complete spaces is complete. Strict inductive limit of a sequence of complete locally convex spaces is complete. The proof contains several tricks. The first trick is that instead of proving explicitly that every Cauchy net converges, we will show that every point in the completion of the space actually belongs to the space. So let X be our space. This is the strict inductive limit of a chain, countable chain of spaces Xn. All Xn are complete. And as usual, we assume that our connecting maps are just inclusions because they are logically injective. So we might identify each Xn with a subspace in Xn plus 1. And we also know that all of them are naturally embedded into X. And moreover, the topology on each of them is exactly the topology induced from X. This was proved some time ago when we discussed strict inductive limits. Okay, so let's introduce some notation. Let script U denote the family of all absolutely convex neighborhoods of 0 in X. We choose any point, little a, in the completion. And we let script F denote the family of all sets of the following form. We consider all absolutely convex neighborhoods of A in the completion and intersect them with X. So here V runs over the family of all absolutely convex neighborhoods of A in the completion. So now we have the following lemma, a lemma inside the proof. I claim that there exists a natural number n such that for every f in script f and for every neighborhood u in script u, their sum f plus u has a non-empty intersection with xn. Before we prove the lemma, let's try to understand why it is useful. So assume for a moment that lemma is already proved. And take any neighborhood W of A, the neighborhood of A in the completion. It's easy to see that we can always find f in script f and u in script u such that their sum f plus u is contained in w just by continuity of the sum operation in x tilde. So f is the intersection of a neighborhood of a with x. U is a neighborhood of 0 in x, so it is also an intersection of a neighborhood of 0 in x tilde with x. And the continuity of the sum operation in x tilde implies the existence of f and u. But we have assumed that the lemma is already proved. So the intersection of f plus u with xn is non-zero. And this implies that the intersection of xn with w is non-zero. Non-empty, sorry. Non-zero, not non-zero, but non-empty. This intersection is non-empty. Since w was an arbitrary neighborhood of A, we conclude that A belongs to the closure of xn in x tilde. But xn is complete. Xn is complete. So it is closed in x tilde. And so we conclude that A actually belongs to xn, and moreover it is contained in x. And so this completes the proof of our theorem, modulo the lemma, of course, because we have started from an arbitrary point in the completion and deduced that A actually belongs to x. So now to complete the proof of our theorem, we have to prove the lemma. Well, let's prove the lemma. Proof of lemma. Well, suppose this is not true. We suppose that for every n, there is a set fn in script f, and there is a set un in u, such that their sum has the intersection of their sum with xn is empty. And let's try to get a contradiction. We may also assume that each un plus 1 is contained in un over 2 for convenience. Let's now denote by u the following set. This will be the sum of un intersected with xn from n to infinity. Well, probably I have to explain what I mean by an infinite sum here. I just mean the collection of all finite sums, ui from 1 to m, where ui belongs to big ui intersected with xi, and m is an arbitrary natural number. So we'll consider the collection of all such finite sums. And let's observe that u is a neighborhood of 0 in X. Why is it so? Well, clearly it is absolutely convex by construction. Well, not absolutely clear, but this is a simple exercise to show that it is absolutely convex, because every un is absolutely convex. And moreover, its intersection with xn, if we fix n, then the intersection of u with xn contains a neighborhood of 0 in xn, namely this set. And now, by the construction of the inductive locally convex topology, we conclude that u is indeed a neighborhood of 0 in X. Okay. So it is a neighborhood of 0, and this implies that we can find a set f in script f such that f minus f is contained in u. Actually, this is a little exercise, because formally f is not a neighborhood of any point in X, but f is a neighborhood of A in the completion. Not exactly neighborhood, but the intersection of a neighborhood of A in the completion. And u also is an intersection of a neighborhood of 0 in the completion with the space X itself. And since the minus operation is continuous in the completion, this implies the existence of such a set F. Okay, so let's now take an arbitrary point in F. Choose an arbitrary point X in F. And let's choose a natural number n such that X belongs to Xn. Well, X is the union of all the spaces Xn, so little x belongs to some of them, if n is big enough. So what to do next? Well, roughly, the idea is the following. So X sits in here, so it sits in F, and moreover it sits in Xn, and this implies that, this inclusion implies that X belongs to F plus U. If we will be able to prove that X actually belongs to Fn plus Un, not just to F plus U, but to Fn plus Un, this will be the contradiction. Because on the other hand, it belongs to Xn, but on the other hand, it will belong to Fn plus Un. And by assumption, the intersection was empty. So let's show that X actually belongs to Fn plus U. To prove this, we take any point y in the intersection of f and fn. By the way, why is it non-empty, the intersection of these two sets? Well, let's recall that each of them is the intersection of a neighborhood of A in the completion with X. So first we intersect two neighborhoods of A, and we get a neighborhood of A, and then we intersect this neighborhood with X. Since X is dense in its completion, we see that this intersection is non-empty. So we take Y, and let's write the following simple formula, which is obviously correct. But the first summand sits in Fn, and the second summand sits in F minus F. F minus F is contained in U, so we see that this is contained in Fn plus U. So we see now that X belongs to Fn plus U, and now we have to show that we can replace U by Un. This will be the last step of our proof. So we may write X in the following form. It's a certain point little an, which belongs to Fn, plus a point in U. So let's recall what U is. U is the following sum. So this will be a finite sum from 1 to n, ui, where an belongs to fn, and ui belongs to big ui intersected with x. It would be great to replace here the whole sum by the only one sum, or un. In general, we cannot do it, but we can modify x as follows. Let's subtract the following finite sum, ui, from 1 to n. Then in the right hand side, we get an plus the sum ui, where little I is bigger than n. So this element belongs to xn, because x belongs to xn, and all the summons ui, since I is less than or equal to n, we see that ui belongs to xi, and so it belongs to xn. The right hand side belongs to the following set, so it belongs to an plus, well, un plus 1, un plus 2, and we have finite and other summons, un plus k, where k is m minus n. Un plus 1 is contained in un over 2, so the whole sum is contained in an plus 1/2 un plus 1/4 un, and so on. But un is convex. So the convexity of un implies that the whole sum is contained in an plus un. And an is an element of fn, so this is contained in fn plus un. So we see that, well, our goal is not achieved. X is not in fn but in un plus un, but a modified element, x minus all infinite sum, belongs to xn and belongs to fn plus un. And this is a contradiction, because this intersection was assumed to be empty. So we see that it's non-empty, and this completes the proof of our lemma. A bit technical, but in my view it's rather nice. The idea of this proof is due to Gottfried. Okay, so as a corollary we see that, for example, the space of compactly supported continuous functions on a second countable locally compact space and the space of smooth compactly supported functions on an open subset of Rn are complete. Because they are strict inductive limits of complete spaces. This one is a strict inductive limit of balanced spaces, this one is a strict inductive limit of Frisch spaces. Okay. So that's all I wanted to tell you about completions. And our next goal will be just to discuss tensor products of locally convex spaces. Today we start with tensor products of semi-normed spaces. I'd like to stress that a semi-normed space is not a special case of a locally convex space. Because a semi-normed space assumes that we have a fixed semi-norm. And tensor products of semi-normed spaces are not special cases of tensor products of locally convex spaces. Because there is a metric aspect here. So today we discussed tensor products of similar spaces, and at the next lecture we apply this construction to local convex tensor products. So to begin with, let's discuss some general facts on bilinear maps. Suppose that x, y, and z are locally convex spaces. So I'll introduce the following notation for the space of all bilinear maps from x cross y to z, which is the space of all continuous bilinear maps. From x cross y to z. Here, when I say continuous, I mean continuity in the usual topological sense, that is the so-called joint continuity. Jointly continuous. Sometimes, not today, but a bit later, we'll also need to consider separately continuous bilinear maps. That is, those bilinear maps which are continuous in each variable. But today, such separate continuity will not be useful, so we'll consider jointly continuous bilinear maps. Well, first of all, we have the following simple result, which characterizes continuity for bilinear maps in terms of similarities. So suppose we have three local convex spaces, x, y, and z. And suppose that P, Q, and R are three defined families of similarities on x, y, and z respectively. And for convenience, let's assume that P and Q are directed. Suppose that P and Q are directed. We know that every family of similarities is equivalent to a directed family, and sometimes directed families are more convenient. So we suppose that P and Q are directed, and suppose we have a bilinear map. A bilinear map. Phi from x cross y to z. I claim that it is continuous, even only for every similar little r from r, there exists a positive constant c, and there exists a similar p on p from p and q from q, such that the following inequality holds. R of phi of xy is less than or equal to c p of x q of y for all x and y. The proof is an exercise for you. Actually, it is a natural version of continuity criterion for linear maps. And the proof is very much the same as in the case of linear maps. Okay, so from now on, we suppose that our spaces x, y, and z are similar spaces. And suppose that we have a bilinear map from x cross y to z. We define the operator seminorum, of phi to be the following number. This is the supremum of the norms, phi of xy, where x and y run over the closed unit balls of x and y respectively. Well, this is a non-negative number. In the general case, I don't claim that it is finite, so it can be equal to infinity. Then we have the following simple proposition. Proposition 2. First of all, I claim that the operator seminorum of phi is finite. if and only if phi is continuous. If and only if phi is continuous. So second, if we now equip the space of all continuous bilinear maps from x cross y to z with the respective operator semi-norm, then we get a semi-norm space. Our initial question is, what is it a normed space? Is a normed space even only if z is a normed space. So in particular, we see that the space of all continuous bilinear forms, that is, bilinear maps with values in the base field K, is a normed space. The proof is again a simple exercise. An important special case of a continuous bilinear map between semi-normed spaces is a bilinear contraction. So we say that a bilinear map phi is a contraction if its operator semi-norm is less than or equal to 1. Such maps can easily be characterized in geometric terms. So we introduce the following convenient notation. Let's denote by U sub x the open unit ball of the semi-normed space X. Yeah. So proposition 3, phi is a contraction if and only if it takes the product of open unit balls of x and y to the open unit ball of z. Or equivalently, we can replace open unit balls by closed unit balls, and the result will be the same. Or we can actually replace only the unit ball in Z by its closure, and again the result will be the same. So again, a simple exercise is to prove this result. And actually, both proposition 2 and proposition 3 easily extend to linear maps. So prove analogs of propositions 2 and 3 for linear maps. In particular, we say that the linear map between semi-normed spaces is a contraction if its norm is less than or equal to 1. The inequality is not strict. In the metric terms, that means that for linear maps, this means that the distance between the images of 2 points is less than or equal to the distance between the points. It slightly contradicts the terminology in the theory of metric spaces, where we usually say that a map between 2 metric spaces is a contractive map if the distance between the images of 2 points is less or equal to a constant, which is strictly smaller than 1, multiplied by the distance between the points. Formally, contraction and contractive map are not the same words, so anyway, this is standard terminology in the theory of normed spaces and in functional analysis in general. The contraction is a map which satisfies this condition. Okay, now we are ready to introduce the following concept. suppose that x and y are similar spaces. We define the projective tensor product. The projective tensor product of x and y to be a pair consisting of a similar space denoted like this. So we write the usual sign for tensor product and write a little pi as a subscript. And a bilinear map theta. So here x tensor y is a similar space. And theta is a bilinear contraction from x cross y to the tensor product. It's a bilinear contraction such that it satisfies the following universal property. So let's draw a picture. This is theta. This is theta. Such that for every seminorm space Z, this is Z, and for every bilinear contraction, so a little big phi from x cross y to Z, there exists a unique linear contraction over phi from the tensor product to Z such that the diagonal commutes. And in the situation we say that little phi is a linearization of big phi. Phi is the linearization of big phi. So roughly the definition means that the projective tensor product is something which enables us to linearize bilinear contractions. Let's now give the same definition, but slightly more category theoretic terms. So we introduce the following category. That's denoted by S norm 1. So the objects of this category are seminorm spaces. And the morphisms are linear contractions. Well, it's easy to see that the composition of two linear contractions is a linear contraction, so this category is well defined. And why is it useful? Let's observe that that isomorphism in this category, isomorphism in this category S norm 1 is nothing but an isometric isomorphism. Well, indeed, a map between two seminorm spaces is an isometric isomorphism, if and only if it is bijective, it is a contraction, and the inverse map is also a contraction. So this means that this is exactly an isomorphism in this category. We can now give an equivalent definition of a projective tensor product. The projective tensor product of two seminorm spaces X and Y is a seminorm space X tensor pi Y together with the following natural isomorphism, between the set of morphisms in the category S norm 1 from the tensor product to Z, and this set of all bilinear contractions from X cross Y to Z. So both sets are actually functors of the variable Z. So here Z runs over the class of objects of our category. And we have a natural isomorphism, that is the natural equivalence between these functors. A simple exercise is to show that the definitions are equivalent. In particular, any of these definitions implies the uniqueness of the projective tensor product. If we have two tensor products, two projective tensor products of the same pair of spaces, X and Y, so let's denote them in a slightly different way. This is theta, and this is theta prime. When there exists a unique isometric linear map, there exists a unique isometric isomorphism between the tensor product such that the diagram commutes. This is immediate from the definition. Okay. Now let's, so it's clear that the tensor product exists, if unique if it exists. But why? Let's not prove that this tensor product exists. So we give an explicit construction of the projective tensor product. First of all, the underlying vector space will be just the algebraic tensor product. Underlying vector space is just the algebraic tensor product. And theta is the canonical map from X cross Y to the tensor product. So now we have to define a seminorm of the algebraic tensor product. So we give the following definition. The projective tensor seminorm, on the tensor product is given by the following formula. If U is an element in the tensor product, we can consider all representations of U in the following form, in the form of finite elementary tensors. Of course, there are many such representations, but for each of them we may form the following sum. And now we take the infimum over all such representations. And this is, by definition, this is the projective tensor seminorm. A simple exercise is to show that this is indeed a seminorm. On the tensor product. Well, why is it natural? Let's observe that if we have a seminorm on the tensor product, such that theta is a contraction, then for each such representation of U, well, first of all, the seminorm of every elementary tensor xi tensor yi should be less than or equal to the product of their seminorms, because theta wants to be a contraction. And so, by the triangular inequality, the seminorm of U must be less than or equal to this sum for every such representation. And what we do is just take the infimum over all such sums. So this sounds reasonable. Now, a few words about the history of this notion. Actually, tensor products of abelian groups were first introduced in 1938 by Whitney, who is most famous for his works in differential topology. And what is much more surprising is that in the same paper, Whitney actually introduced the projective tensor seminorm. Projective tensor products were further developed by Schatten in 1943 and later by Grothendieck in the 1950s, who actually created the whole theory of topological tensor products of Banach spaces and of locally convex spaces. Okay, let's now give a useful geometric interpretation for this seminorm. First of all, we need the following notation. Suppose that S is a subset of X and T is a subset of Y. Then we define their circle product, denoted like this, to be the set of all elementary tensors, X tensor Y, where X runs over S and Y runs over T. So this is a subset in the tensor product of X and Y. In the literature, sometimes this set is denoted by S tensor T. But, well, this notation is standard, but it is not, it is not good for the following reason. If S and T are vector subspaces of X and Y, then the circle product is obviously different from the tensor product of S and T as vector spaces. Because the tensor product of S and T in this case consists of all finite sums of such elements. So that's why I'm using a slightly different notation. Okay, now we have the following result. Proposition. The open unit ball in the tensor product with respect to the projective tensor seminorm is nothing but the absolutely convex hull of the circle product of the respective unit balls in X and Y. Or actually, we can just take the convex hull of the same set, because it's easy to see that the circle product of two unit balls is circled. So it suffices to take the convex hull of the circle product. So as this equality readily implies that the projective tensor seminorm is nothing but the Minkowski functional of this convex hull. And this also shows that the projective tensor seminorm is a rather natural number, so a natural function. Well, indeed, if we now come back to our canonical map theta from X cross Y to the tensor product, so we remember that theta wants to be a contraction. But if we have a norm on a seminorm on the tensor product such that theta is a contraction, then the circle product of these two balls has to be contained in the unit ball of the tensor product. But the unit ball is convex, so the convex hull also has to be contained in the unit ball.
So now we define a semi-norm in exactly the way that this convex hull is exactly the unit ball. So that's the reason why we define this projective tensor semi-norm in this way.
So anyway, we will use the following notation. The algebraic tensor product of x and y equipped with the projective tensor semi-norm will be denoted like this. Now this notation is consistent with our original definition of the projective tensor product for the following simple reason. This space, together with the canonical map theta, is exactly the projective tensor product in the sense of our abstract definition of x and y. Well, indeed, why is it so? Well, first of all, we have already observed that theta takes the product of unit balls in x and y. Well, clearly it takes it to the circle product, which is contained in its absolutely convex hull. And this is nothing but the unit ball of the tensor product. So this implies that theta is a contraction for the projective tensor semi-norm. You can now come back to our picture. Let's draw it once again. This is theta. So suppose that phi is bilinear contraction. Now, since if you now forget about semi-norms, so we have the pure algebraic picture. This is the algebraic tensor product of x and y. Clearly, we can linearize big phi. So phi is the linearization of a big phi. Clearly, it exists and it is unique. This follows from the algebraic theory, algebraic properties of tensor products. It exists and it is unique. And now we have to show that little phi is also a contraction. Well, indeed, big phi satisfies the following condition. So this conclusion is equivalent to the fact that big phi is a contraction. The diagram commutes, so this implies that little phi takes the circle product of ux and uy to the ball, to the open unit ball in Z. But since the open unit ball is absolutely convex, they conclude that phi takes the absolutely convex hull of the set also to the unit ball. Because phi is linear, and well, because phi is linear, and because we have this inclusion. So this implies that little phi is a contraction. And this completes the proof. Oh, sorry. Okay. Okay, so that's all for today. And at the next lecture, we will discuss a general notion of a reasonable semi-norm on the tensor product. And we will see that the projective tensor product, the projective tensor semi-norm, has the property of being the greatest reasonable cross semi-norm on the tensor product. Then we will introduce another seminorm of the tensor product, the so-called injective tensor seminorm, and we will show that the injective tensor seminorm is the smallest reasonable cross seminorm on the tensor product. And of course, we discuss some concrete examples, and then we use this construction to define projective and injective tensor products of locally convex spaces.
Не сядь.